Hello, so today I'm going to introduce the computer program that I've been using for a while to monitor and to communicate with my mobile robots. This software is called the Robot Monitor Program. I developed this Robot Monitor Program using Visual Basic.net. So unfortunately, this also means that the software can only run on Windows operating system for now. The robot and the software communicate using Bluetooth wireless link. Let me just turn the robot over. I'm going to take out the battery module, and you can see over here, this is the HC05 Bluetooth transceiver. So the Bluetooth transceiver will appear as a virtual COM port to the software. At the moment, the robot will transmit a data packet consisting of 64 bytes 20 times a second, or every 50 milliseconds. So this 64 byte will contain things like the identification of the machine, the settings, and also the values of all the onboard sensors. So the user can select a subset of this sensor parameter and display on the various windows on the software. Let me just turn on the robot. So I'm going to pair to the machine. So you can see on the main windows, this is where I can send some commands to the robot, and on the right hand side, these are the slider bar. I'm actually using this slider bar to tune the feedback control parameters that control the balancings. So this is how I tune the coefficient for the balancing algorithm. I'm using, by the way, I'm using state feedback, or what we also call this the LQR method. There are two XY windows at the bottom. So this XY window is similar to an oscilloscope display, where you can show the sensor parameter versus time. Each XY display can show 4 different parameters. There's a rectangular window, so this is the pose of the robot. In robotics, the pose means the XY position of the robot, say on a 2-dimensional plane, and also the orientation or the direction of the robot. There's another smaller windows here. This is the FFT. So this fast Fourier transform is an algorithm that runs on the robot. I am able to select a particular sensor values and feed it continuously to this FFT algorithm on the robot firmware. So this allows me to analyze the spectra of that particular sensors, and this is useful for predicting the states and the behavior of the machine. Now let me just make the robots upright. So now it is self-balancing. So as you can see on the XY plot, these are showing the status of the sensors. So let's start with this XY plot on the left hand side. The white color trace shows the instantaneous average velocity of the wheels. The blue trace is showing the distance traveled by the wheel. So let me just push the robot backwards. You can see that the white trace goes to negative, and the blue trace also decrease, indicating the distance is decreasing. Now I push the robot to the forward. You can see it is moving forward. It's indicated by the white trace. The blue trace also show increment in the distance traveled. Right, so let me just push it. The yellow trace on this XY plot actually indicates the tilt angle of the robot. Let me shut down the motor driver. So I do this by engaging the test mode. So now I turn on the motor driver. So right now I'm tilting the robot to the front. You can see the yellow trace show positive value. Tilting to the back, so it shows negative value. So front again, back, front, back, front, back, front, back, right. Let me turn on the motor driver again by engaging the normal mode. Okay, so now the robot is self-balancing again. The other XY plot, I can select some parameter to show, for example, there is a infrared distance sensor at the front of the robot. So this is indicated by the yellow trace. As the object is near to the sensor, then you can see the value decreases and so forth. So other traces on this second XY plot, the white and the blue trace indicates the onboard, the temperature sensor and the battery voltage level. The red color on this second XY plot is showing the voltage applied to the motor driver. So when I push backward, then the motor is negative voltage will be applied to the motor driver and vice versa. For example, now let me just illustrate the tuning. These two parameters actually change the offset voltage applied to the motor. So if I just shift it from the default value, which already properly tuned, you can see the robot will vibrate. If it's too small, then you will also shift. The robot cannot stay at the set location. So let me just set it back to the default. This windows, the pose of the robot actually indicates the XY position and also the orientation. Let me just illustrate it by moving the robot backwards, and you can observe the icons. So the icon moves backwards. I move it to the front. So the icon moves forward. Let me move it backward again. Okay, so I'm now turning the robot to the left, turning back to the right. So there are 3 dots. So this dot indicates the front side of the robot, and the dots also indicates the status of the camera or the machine vision module. So on the head of the robot there is a CMOS camera, and at the back there is a small circuit board with a 32 bits processor. It's running some algorithms. I have implemented a simple neural network that can estimate whether there is an obstacle in front of the machine. So the status of this, the output of this neural network is indicated by the 3 dots. Green color means that there are no obstacles. I'll watch as I move my hand across. Red means it detects an obstacle in front. So also this white color LED will light up when obstacle is detected. Okay. Finally, this FFT display. So right now I'm feeding the average velocity of the wheels into this FFT algorithm. So it actually can indicate the spectra of the velocity. This will be very useful. For example, now this machine is standing still, no disturbance. When it is being disturbed, so the spectra would provide an indication of the type of disturbance and so forth. So the source code are on the GitHub page. You can actually find the link at the description below this video.